This is a lecture on the integrated rate law formulas. I'm going to derive three of them: first order, second order, and zeroth order reactions, and we're going to come up with the integrated rate laws. And the reasoning we need to do that is because right now, if I have, for instance, an A becoming a product, and I write the rate law, and if this is the elementary step, let's say I say the rate law is equal to K, of course, times the initial concentration of A to the first power, because there's only one of them there, and it depends upon how many are reacting. So this is a first order reaction. Now, understand that the rate equation only tells me something about the initial conditions. So really all it tells me, the rate, which is how much I'm making the products or how fast the reactants are disappearing, is only based on the initial condition. So we have rate over time, and obviously it's going to go down. As we use up A, okay, the reaction rates decrease, obviously. So, but all we have is the what? The initial condition, the initial rate. After that, all bets are off. We'd have no way of getting that. So there has to be a way for us to be able to figure out what the rate is at different times. And of course, that is what a derivative is. Now, what a derivative is, as people have said, and I hear this all the time, I hear people say, well, it's the rate of change. And I always ask, well, what does that mean? And they don't know what that means because they're so used to learning vocabulary. To get a derivative, before we get a derivative, people talking about averages. So let's take this point here at time 1, and this point here at time, I don't know, make it 4 seconds. And people would make an average. Now, when you make an average, you're assuming that there's no change between those points. And as you can see, we'd be overestimating the value of the rate because this kind of exponentially decreases. So to get a better average rate between those 2 points, to get some information, what we do is make these points smaller. And that's what a derivative is. You'll see, okay, dx, dt, and you'll see all this different types of written designations. But this little d here would mean the differential of r, okay, or in this case, we'll say r in this case, over the differential of time. And what does the d differential mean? It means that I'm going to take a point. In fact, I'm going to take 2 points, and I'm going to take those points with the limit going to 0. What that means is I'm going to take a super tiny 2 points that are so small they're essentially almost the same point. So I'm going to make these points smaller, infinitely smaller, with the limit to 0. What does that mean? Well, I'm taking something called a differential. A differential is a difference between 2 points. So we're taking a differential, 2 points, with their limits approaching almost 0. So they're just about what? Touching, okay? As close as they can get together without touching, the limit to 0 is infinitely small. And that's what that means. And then I'm going to take the differential of time. So I'm taking the differential between 2 points in the y-axis as I approach 0. And then I'm going to take the differential in the x-axis. So dr dt is what that means. And getting a derivative really means that I am getting a point in time. I'm getting an instantaneous rate of reaction at some time period. So if you have a time period, I can find that time period. Now, of course, what it really is, also, as people have said correctly, it's the change of y over the change of x, which we know, of course, is slope. So this is a slope of the line. And of course, if this is the point, or that differential 2 points that are approaching 0, as we really say, as we say, is the slope of that point in that time is right there. Okay, and I'm just drawing a tangent line through that, as you might have heard. But of course, as this time changes, so does the slope. The slope is constantly changing because this is not a straight line. And that's where calculus comes into play. We're dealing with values that are constantly changing. They're not staying constant. So we have to have a way of working with those things. Now, so the derivative gives me instantaneous rate at a certain time period. I guess that's useful, but as soon as I get that piece of information, that time has changed. So as interesting as instantaneous rate may give me, as a chemist, that's still not enough for me. What I'm really after is how much concentration is left after a period of time. If I'm thinking about like a bottle of hydrogen peroxide, and I know hydrogen peroxide is going to decompose into water vapor and oxygen. And over time, it has a negative delta G, which means this is definitely a spontaneous reaction. So what happens over time? Well, I want to know how long the shelf life of this chemical is. How long will it take? What is the time? And how much concentration of A? I'm looking for how much A, not necessarily the rate. Rate just tells me how much is being used up and how much is being made of the product. It's not telling me exactly how much is left. It's just giving me a flow rate, so to speak. And that really reminds me of another important analogy. And not something that I came up with. It's a very famous analogy. If you take a water spigot, let's say that's on the outside of your house, connected to a water. So this is coming off the side of your house, right? And here we have a bucket. All right, it's the best I can do with my artwork. Now, if I've got, let's make it red water coming out and filling this bucket, as I turn this valve, okay, as I turn the valve to open it, this red water comes out. And let's pretend that we're turning that valve and we're accelerating the turn so that different amounts of water is coming out. We're increasing the flow rate as we turn the valve. So the flow rate, okay, lets us know exactly, okay, the rate of water that's coming out. But does that tell me anything about how much water total in the bucket? No, it doesn't. See, the rate at an instantaneous time tells me the rate of which I'm losing A, which is the same thing, the rate I'm losing my red water. But it doesn't tell me how much is in the bucket. So what I need to do is I need to do something called an integral. I have to integrate, okay, in order to figure out how many. Now, what an integral is, and it's really the opposite of a derivative. Some people call it the antiderivative, but what an integral does is it basically adds up all the little, I should say, differentials. Just to make things simple, if I've got a function, and let's just make the function look like something like this for right now. So this is f of x, and that's my function. All right. Now, the derivatives, of course, would be for a value of, let's say, x at some value of y. Okay, I would know exactly what my slope is at that point, my rate of how x is changing with y. And of course, you can see that from over here, it's coming down again. So it's changing over time. So my rate is changing. But if I want to know exactly how much y from one point to another, what I need to do is basically take the differential of dx, or dx, the differential of x, which is, as we said before, it's 2 points that are coming close in contact. We're approaching 0. So we're taking 2 points that are essentially a 1 point, right? They're just approaching that 0 in between. We're trying to find that smallest sliver, okay? And what we're going to do is we're going to add all these slivers. So this is one sliver. You can think about these being like triangles. Rectangles. So, of course, if I zoom this up bigger, okay, those rectangles will be smaller than this. But you can see that I'm going to add up all these rectangles. Now, of course, if these rectangles are infinitely small, we won't have this error right here. So if we approach the limit to 0 and make this differential, which is the distance between these 2 points, which is essentially a tiny, 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 tiny slice, and I make an infinite number of slices that are triangles, I can come up with, and sum these guys together, I can find the total amount of y that exists under this curve. And you say, well, okay, that sounds interesting, but how does it help me as a chemist? Well, if I'm trying to figure out how much water is coming in, think with me for a second. If I have time and I have concentration now of A, which is my reactant, and I know that concentration goes down over time, all right? And I don't know the function, I'm just guessing here. But if I know that I have a derivative at a certain t, and I want to know from this point to, let's say, this t, okay, what I can do is I can figure out, by integrating, I can figure out how much the A has changed from this position because I'm adding all these slices together. I'm finding all of this, quote, area under the curve. But more importantly, we need to find a way to evaluate, hey, at a certain t, let's make it this t right here, what is the value of A? That's powerful. So by integrating, I have a way of finding this exact slice at t, which will measure exactly how much of A I have left. And I can figure out how much time. So integrating will help me figure out how much water is actually flowing. And there's some really important analogies in science. We know that velocity, okay, velocity is basically distance, speed over time. All right. And we know when you go from velocity to acceleration, okay, which is going to be essentially velocity over change of time as well. So the change of velocity over time, that's a derivative. And if I want to go from acceleration back to velocity, I would do an integral. I'd find how much speed. And if I want to do an integral of velocity, I would find the total what? Distance. See, the distance or displacement, okay, over some time becomes velocity. So the change of your displacement becomes velocity. So this is a derivative as we go from distance to velocity to acceleration. And as we go back, it becomes an integral. So so if you think about it, the total distance you travel is the integral of velocity. All right? And the total speed that you were going is an integral of acceleration. So the total amount of water that we're working with here is an integral of the flow rate. And the flow rate is a derivative. It's a rate of change. Okay? If we get back to my flow of the water analogy, which is not mine, by the way, very famous. The flow rate is the rate of change. And if you say the flow rate, let's say it's 2x. Let's make that 2x. That's the flow rate. And that's the slope, the flow of the time, which means about a time of 2 times x, the flow rate, or the rate of flow, or the rate of reaction is 4. If it becomes 3, then it becomes 6. So you can see my rate is not constant. It keeps changing. So what calculus helps us do is use values that are constantly changing and do multiplication or summing however you want. Now, if you look at how fast water is getting in, doesn't mean we're measuring how much volume of water. So if I take this rate of change of flow, which by the way is a derivative, and I integrate it, and I add up all the drops of water, the red water coming out, I get a volume. And that's what integration does. It adds how much water is coming up. And our 2x becomes x squared. Remember, the derivative of x squared is 2x. So the integral of 2x is x squared. Integrals and derivatives, okay, are just mere opposites of each other. But look what's happening here. I'm getting total volume that's exponentially growing, x squared. So if my rate is 2x, I integrate that, I get x squared, which is showing me how the volume is changing. At time 2, that's important, at this time, I've got a volume of 4. At time 3, I got a volume of 9, and that's what we want as chemists. We want to measure the drops of water, or in this case, the what? The little integral, or I should say differential, tiny little slices. And that's what we want. We want to measure, hey, what is the concentration of A at a certain time period as the reaction goes forward? Not so much water, but it's the same thing. So let's get to the first derivation, and this is the backbone of understanding the calculus behind this.